All right, my friends, welcome back. Happy Friday. Boy, it's been a whirlwind. It feels like every time we meet, there's 5 or 6 more reactions to do, and there's a lot to keep track of. People have asked, how do I manage all of these details? If you go to the content page of Learning Suite, there is a handout for each chapter. And those handouts basically summarize the reactions that we've talked about. So it's all in your notes. It's not new, but I know some of you have anxiety that you have maybe missed something. And so most of it's there. Let me just add, I've been very careful in class to say what you needed to know and what you don't need to know. These handouts are kind of old, so anything I've said about mechanism in class supersedes what's on the handouts. For example, I told you for the Chapter 9 handout, the Chapter 9 reactions, that I don't care that you know how SOCl2 turns OH into a good leaving group. All I care about is that you know that it becomes a good leaving group and then chloro displaces that good leaving group from the backside via SN2 reaction. So there's some details listed over here that maybe are interesting but that we didn't talk about in class. So just use your intuition in your notes to help you understand, but they're at least listed there. Okay, so last time, where we go? There we are. Last time we were talking, we finished up hydroboration oxidation of alkenes, and then I showed you 2 new reactions of similar reagents that you've seen before. In fact, you shouldn't think about these as new reactions. It's the hydration of alkynes and the hydroboration oxidation of alkynes. The hydration of alkynes gives you an enol with the more substituted carbon bearing the OH and the less substituted carbon with the hydrogen. We said that stereochemistry doesn't matter here. Whereas hydroboration oxidation gives you an enol where the OH is on the less substituted carbon. Do you see how you don't, if you think about this by analogy to the alkene chemistry, this isn't new. The OH goes to the same place, the less substituted carbon versus the more substituted carbon. What is new is what I told you, that the enol isn't the most stable form and that it in fact tautomerizes to the more stable keto form, the isomer or the tautomer, which has the double bond between carbon and oxygen, and then the hydrogen on the other carbon. And some of you were worried about, well, do I show the enol or the aldehyde as the product? You show the aldehyde. But that said, I'm not going to give you a situation where both of these are options and you have to guess what I'm thinking, okay? So the correct product for hydroboration oxidation is the aldehyde, starting with the terminal alkyne. The correct product, starting with the terminal alkyne for hydration, is the ketone. And I showed you the mechanism of tautomerization, but it was sort of towards the end. You can tautomerize from enol to ketone in under either acidic or basic conditions. It works both ways. So I'm showing you examples of both of those. When we do acid catalyzed alkyne hydration, of course we're under acidic conditions. So this is what it would look like. The pi bond between carbons A and B attacks the hydrogen. This should be familiar. This is like the first step of alkene hydration. Pi electrons attack the anti-bonding OH orbital. You create a new carbon-hydrogen bond with less substituted carbon B, so that the positive charge can be on more substituted carbon A, where you have the benefit of resonance stabilization of that positive charge with the adjacent lone pair. And so this intermediate has a resonance structure that looks like this. And now you can see where the carbon-oxygen pi bond comes from. You can get to that from either resonance structure. From the one on the top, you have water, remove a proton from the oxygen, electrons kick down and form a pi bond here. This looks very much like an E1 type reaction. We're removing a proton that's beta to a positive charge. In contrast, the one below looks just like a typical acid-base reaction. Water removes the proton from the positively charged oxygen. You get your ketone product, which we've said is more stable than the enol, and that's why it forms. And this process of going from enol to ketone is tautomerization. Go ahead.
So let's say you have a reaction where the answer in quotation is the chemical on the left, and you do not state in the question that it is in acidic or basic conditions. Would that be the final product?
Good question. If you got here and it was not clear that you were under acidic or basic conditions, should that be the final product? No, because if you look at the reaction, it actually is clear that you're under acidic or basic conditions. And in any case, the enol, even in pH 7 water, will tautomerize to the more stable keto form. What I'm saying is, because it's catalytic, you don't need very much acid at all to make it happen. Okay. Similarly, under basic conditions, tautomerization involves first deprotonation of the enol to give this conjugate base of the enol that's called an enolate. And I showed you how the enolate has a negative charge delocalized between the oxygen and the adjacent carbon. And that if you protonate on the adjacent carbon, that gets you to the aldehyde or the keto form, the tautomer that we've been talking about, where you now have a carbon-oxygen double bond. And you can do this from either of the two resonance structures. Either way is correct, so pick one. You can have electrons from the oxygen kick down and then electrons from the pi bond remove a proton from water with the new proton going on less substituted carbon A, or more substituted carbon A. Or you can go to the other resonance structure of the enolate where the negative charge is on carbon A and then just protonate directly on carbon A. Both of those options, totally fine. Okay. Tautomerization, you can tell when you're doing tautomerization because the only thing you're doing is proton transfers. Okay, you deprotonate something, you get to a resonance stabilized intermediate, then you protonate on a different carbon. Or you protonate something first, you get to a resonance stabilized intermediate, and then you deprotonate on another carbon. So tautomerization can happen with just simple proton transfers. These two reactions, hydration of an alkyne and hydroboration oxidation of an alkyne, are not on that chapter 10 handout. I should add them, but I'll just tell you they're here on the notes, so add them to the handout in your mind or on a sheet of paper, and you'll be responsible for them. Go ahead.
Can we consider tautomerization when it's like the enol product with alkyne?
So can you consider tautomerization if the enol product is from an... Can you try again, because I'm not understanding the question, sorry.
I'm just confused if like tautomerization works in all the other reactions we have, like copper.
Okay, so does tautomerization work with any of the other reactions that we've had? No, because none of the reactions we've had so far give you an enol, that is a double bond with an OH on it. But henceforth, any reaction that has an enol as a product, you're going to be thinking, okay, it better tautomerize to the more stable keto form. One quick thing, how do you remember that you get the aldehyde from the hydroboration oxidation versus the ketone from hydration? Just remember that more substituted, less substituted carbon thing. Hydration puts it on the more substituted carbon, so that by definition gives you the ketone. Hydroboration oxidation puts the oxygen on the less substituted carbon of the alkyne. By definition, that gives you the aldehyde. All right, anything else we need to say about that? Okay, well, we want to introduce you to the world of synthesis. And this is something now that you've got a toolbox of reactions, about 2 or 3 chapters full. You can start to stitch together reactions that you've done before to create new and interesting molecules. And this is the whole reason why, one of the main reasons why anybody wants to do organic chemistry anyway, because at least in the United States, we have this idea that if something's wrong with you, you ought to be able to take a medication to fix it, right? Or take a pill to fix it. Well, who makes the pills? Who discovers the molecules? Who synthesizes them? There's a lot of different ways you can discover biologically active molecules. One is by just looking for molecules in nature. That's called natural products chemistry. But sometimes you find an interesting product in nature, but you can't isolate it from nature in large enough amounts to get enough molecule to use it as a medication. And that's where synthesis becomes necessary. For example, if you want to learn more about that, look up the history of the drug paclitaxel or Taxol. This is a drug used for breast cancer, and it was discovered as a natural product in the bark of the yew tree, but they couldn't get enough of it from the yew tree to make a reasonable amount of drug, and so it had to be synthesized. And so being able to use reactions to make complicated natural products is really important. So we're starting out fairly simple. We're not going to synthesize any particular drug molecule here, but the strategies that you learn are the kinds of ways people think of when they're thinking, how do I synthesize something more complicated from simpler starting materials? So a typical synthesis problem starts something like this. Here is your target molecule on the right. This is what you want. Why do you want that molecule? I don't know. I think that molecule is probably useless, but we're pretending that it does something interesting that we want, okay? Trying to develop the strategies. And then where do you start? In practice, where you start is an economic decision. You source starting materials. It's a supply chain issue. What precursor to this, if I can't buy this molecule for cheap, if I have to make it from simpler precursors, then what are the simplest precursors that I could start with? Are they available, and how expensive are they? Now, you might ask the question, well, could I start with something that's only a little bit different from this and then call my life good? And the answer is sure, but we're supposed to learn something here. So we're going to make it a little bit harder, and we're going to pretend that the only starting materials you have in your supply chain are ethanol, a 2-carbon alcohol, and then this epoxide, which is called ethylene oxide. And we'll learn how to make ethylene oxide, if not today, then on Monday. But right now, these are your 2 starting materials. And you have to make this product. So one of the skills that you want to learn is the skill of retrosynthesis. Retrosynthesis is not like synthesis in the 70s, or for you guys, retro is like, I don't know what, the early 2000s or something like that. Retrosynthesis means thinking backwards. Before you do a synthesis in the forward direction, often if you try to start at the beginning, which is the place that you think you should start, there are too many possible ways you could take things. And so instead of starting at the beginning, what we do is we start at the end and we think backwards, looking for structural patterns, thinking backwards to what we think the final reaction was that generated this molecule, okay? So this is going to be new to you, and you can think of retrosynthesis as like the spiritual creation of your synthesis. You have an idea of where you want it to end, but you don't know how to get there, so we're going to think backwards. And after we think backwards a few steps, then sometimes we'll just go to the beginning and think forwards and connect the two chains, and then we have a plan. So, two things to start with. First, focus on carbon-carbon bonds. Because that's where you build complexity in the molecule. And that can give you a sense of what you have to do. For example, as I look at these two starting materials, I see that they each only have 2 carbons. They come in 2 carbon chunks. In contrast, when I look at my product, I realize that my product has 6 carbons. So that means I'm going to need to make at least 2 carbon-carbon bonds. Now you could imagine some weird convoluted strategy where you would be like, well, I want to break these up first into 1 carbon pieces, then I'll stitch together 6 1 carbon pieces. That's a terrible decision. You should use the carbon-carbon bonds you already have, right? So what I'm going to suggest is that we indicate on our target molecule which carbon-carbon bonds we think we're going to have made. And those will be bonds between 2 carbon units. So I'm using the blue squiggly line to indicate that I think these 2 carbons can come from one of these 2 starting materials. I'm not sure which, but I think that they came in a chunk together. And then the bond between that 2 carbon unit and the next 2 carbon unit, I will have had to have made, right? Then I will say, okay, then the next bond between that 2 carbon unit, carbons 3 and 4, and then carbons 2 and 1, that is a bond I have to make. Okay? Does that make sense? Can you see that strategy? If it doesn't, let's talk about it. Sometimes it's hard for me to remember, because I am old and have been doing this for a while, sometimes it's hard for me to remember back when I was you sitting in those chairs. So if something's not making sense, let's talk about it. Okay, once you've identified the carbon-carbon bonds, yes, go ahead.
Yeah, can you go ahead and explain that part again, where we have to, like, looking at the target molecule, where we know which carbon bond came from the starting materials?
Yeah, so the question is, how did I know that I was going to break up the molecule in that way? It really comes from the idea that my 2 starting materials only have 2 carbons in them. So if I want to make something that's 6 carbons long out of 2 carbon units, the simplest way to do that is to incorporate 3 of those 2 carbon units. So it's literally just counting from the end, 1, 2, okay. Then I must have made the bond between that and here, and then the bond between that and there. The idea is that I don't need to make the sigma bond between carbons 1 and 2 because it's already there. So I want to use the carbon-carbon bonds that are present in my starting materials and allow them to still be in the product. I don't know, how is that? Okay, all right. Okay. All right, so once you've identified the carbon-carbon bonds you have to make, now you want to be thinking about strategy. And nothing's going to save you at this stage if you haven't practiced the reactions and have a good sense for what they do. This is why I told you that if you're needing help on reactions, you ought to be thinking of reactions in a couple of different ways. Product reagent, what was the starting material, product, starting material, what was the reagent, and perhaps even this way, product, what was the reagent, what was the starting material. This is the one, if you can get there, that's the one that really helps you with synthesis. So, let me ask a question. And sometimes describing the bond that you're trying to make can be helpful. For example, this is a bond between an sp3 carbon and an sp carbon. It's a sigma bond, but it's a sigma bond between an sp3 carbon and an sp carbon of an alkyne. So now you need to think back and go to your filing cabinet in your brain. And and sometimes, I don't know if you guys, it's a really old cartoon, but you can Google this. There's an episode of SpongeBob SquarePants where SpongeBob forgets somebody's name. And then it zooms into the SpongeBob brain, and there's all kinds of little SpongeBobs running around. What's his name? What's his name? And they're rifling through filing cabinets. Papers are going everywhere, and then the whole place is on fire. So this is what happens to you when you're sitting in the testing center taking my exam. Okay, think through your filing cabinet. I need an sp3 to sp carbon-carbon bond. You're not getting it, you're not getting it, everything's on fire. We want to prevent that, and that's why we're practicing now. Can anybody think of a reaction where you have made a bond between an sp carbon of an alkyne and an adjacent sp3 carbon? Got anything? Go ahead.
You could react to make base with an alkyne.
Okay, so you're thinking I could start with an alkyne of some sort. I could use a base that would give me this acetylide ion, and then what? What do I do with that? You're on the right track because this is a nucleophile. So somebody said carbocation. I think you're probably overthinking it. Is there something you could use that would not require a carbocation? I'm thinking of, go ahead. So you could, so yeah, there's a couple of options here. What if the electrophile was an epoxide? Can strong nucleophiles open up epoxides? Sure. So, and do you see what we're doing here? We're just sketching things down. We're brainstorming. I know you're uncomfortable with that because I know you want an algorithm where you start at the beginning and you just write out the correct answer every time and you never get anything wrong. Sorry, folks, this isn't that class. Instead, you sketch it out, you try some things, you're like, oh, that's not going to work, and then you go back and sketch it again and try it until you get it. Let's see whether this works. Acetylide attacking an epoxide, opening up the epoxide. Does that, I mean, if we called that nucleophile, this is something that you just barely learned, opening up an epoxide in chapter 9. Does that look somewhat familiar to you? Yeah? So let's see what the product of that would be. And remember, we're temporarily not worrying about whether this immediately leads to our product or not. That's the new bond we made. And then here's a negatively charged oxygen. And I'm going to skip the final protonation step that would give us an alcohol. Interestingly, and I've mentioned this before, when you do a reaction where you open up an epoxide with a nucleophile, you get a pattern, a structural pattern, where you have an OH on one carbon and then your nucleophile on the other carbon. That's what I'm going to call a 1,2 nucleophile OH pattern. And if you look for that in the product, that can give you an idea of how to make the bond. Does anybody see that structural pattern in the product? It's right there, isn't it? This is the 2-carbon chunk. Here is the OH. Sorry. Here is the OH. And then right where we want it to be is the alkyne. So, yeah, we just stumbled upon a strategy for making the bond between carbons, green carbons 2 and 3, by epoxide opening. Okay, good, yes?
I'm curious, so, but the alkyne wasn't included in like your starting materials.
Uh-huh.
Did you make the alkyne first?
Yes, so that's a great question. The question is, the alkyne was not an allowed starting material. Because we're not at the beginning yet, we're just thinking one step backwards. This is like time travel. You're allowed to assume that you might have done something else first. So now, if we do this, now we got another problem because now we got to make this. But that's a simpler problem, right? And we can still step backwards and connect that. Good. Okay. What about the bond between green carbon 4 and green carbon 5? That's also, both of these are sp to sp3 carbons. But what about the one over here? You don't have an oxygen. We lack that 1,2 nucleophile OH pattern. So now we got to do something else. Can you think of another strategy that might allow you to make a bond with an alkyne carbon besides the epoxide? Yeah, go ahead.
We could turn the OH to H2O, so we'd be the linear and have the most pair on the carbon.
Okay, great. So you're thinking of something like this. And I'm just going to be generic here with the R group, but we'll start with, again, an acetylide ion. And then you're thinking something like this, a leaving group on a 2-carbon piece, okay? So that's just a simple nucleophile, electrophile. We're changing colors willy-nilly here. It doesn't actually mean anything. And that's a different way. I'm sorry, it's bothering me. I thought I could handle it, but I can't. There we go. That's a different way to make a bond between an sp carbon and an sp3, oh, sorry, wrong one. sp3 carbon, that one. Okay, good. So we're getting a general idea. And both of these methods of making those bonds require us to have made an alkyne. Before we're going to, again, suspend disbelief. We're not yet worried about how to get from the alkyne all the way back to the starting material. But if you're thinking about this, is there one of these two reactions? The first one makes the sigma bond between carbons 2 and 3. The second one makes the sigma bond between carbons 4 and 5. Is there one of these you'd want to do first? And if so, why? Which one of these would you want to do first? Got nothing? Okay, let me help you a little bit. How do you deprotonate an alkyne? What kind of base do you need to do that? Super strong, right? Because the pKa of an alkyne proton is 25, and I don't know why that's green. Okay, so you need a base whose conjugate acid has a pKa higher than 25. So that would be potential candidates. The one that's used a lot, why are we still green? The one that's used a lot is NaNH2 in your text, but you could also use sodium hydride, and that would work too. Now, suppose I made this one first. Suppose this was just a hydrogen. And then after I make this one, I want to deprotonate this hydrogen. Is that going to fly? Why not? Right, because you've got the proton on the alcohol, right? So that's going to interfere with deprotonating the alkyne. So I'm going to propose that we do this one last to avoid OH deprotonation issues. Okay, so now that we've sketched it out a little bit, let's figure out sort of what our plan is. And again, we're going to use retrosynthesis arrows. At some point, it's okay to think in the forward direction, but I want to show you how the retrosynthesis arrows are used. We used a backward sort of double-lined arrow, and everybody in chemistry knows that means you're thinking backwards, okay? So we're going to make this bond between 2 and 3 first. And what I'm going to do is write what kind of reaction it is. Epoxide opening by an acetylide. And then I'm going to draw what the starting materials were, and I'm going to use my sketch here to tell me. So the starting material would have been this alkyne, this acetylide, and then this epoxide. And anytime you have as one of your starting materials an allowed starting material, you should say, yay, achievement unlocked. You get some kind of prize, right? Because you've connected one of the starting materials that's allowed to your final product. Okay, you with me so far? Thinking backwards. Now, some people will not bother to do what I'm doing. They will just draw the fully protonated alkyne. But because we're new at this, I'm going to draw a retrosynthetic arrow from the acetylide to the terminal alkyne. And then I'm going to write the reaction that gives me the acetylide from the terminal alkyne. And that's alkyne deprotonation. That's just acid-base chemistry. And I need a really strong base, so I'm going to write what the reagent was. Okay? All right, so now in our process, we have done this 2,3 sigma bond. And now we've got carbons 3, 4, 5, and 6 to deal with, and we want to make this bond. What's the right starting material for that bond? It should be this simpler alkyne that's deprotonated on one side, and that's going to be carbons 3 and 4. Then how about 5 and 6? What are they going to be? Something with a leaving group. Now, probably the most convenient leaving group you can think of is an alkyl halide. If you used ethanol, remember OH minus is a bad leaving group. In other words, if I use this as my electrophile, all that's going to happen is my alkyne's going to deprotonate it. So, which is why in my plan above, I showed a leaving group there, and it wasn't OH. Fortunately for you, we know how to get that from ethanol. That is a chapter 9 reaction. There are a couple of ways that would work. What's one? PBr3 converts alcohols into alkyl bromides via an SN2 reaction. That would work great. HBr also works. So you can see that doing this is going to be frustrating if you haven't mastered the reactions. That's where flashcards can help you out, because if nothing's going to save you at this point from forgetting, okay, I knew there was a reaction somewhere that turned OH into a BR group, but how do I do that? Okay, so there's another ding, achievement unlocked. We are 2/3 of the way through with this. Now we're thinking backwards, and this is maybe the one that is most difficult for students, but once you've seen it, you can always remember it. Again, going to the, that's getting the deprotonated alkyne or the acetylide ion from an alkyne is simple deprotonation, and you can do that with NaNH2 as an example. All right, but now we've got a slightly more, there we go. A slightly more complicated problem, because now we got to figure out, this is carbons 3 and 4, and we need to figure out how to get to there from here. All right? So, go ahead.
Sorry, with the step that you just barely completed, how do you stop that essentially now ethane group from attaching to both ends of the alkyne?
Right, how do you do this? And the idea is, how do you prevent this from deprotonating both sides? The answer is, with any polyprotic acid, the first pKa is always the lowest and the second one is always higher. The reason for that is that once this is negatively charged, removing the other proton would introduce charge repulsion. So that other proton is no longer acidic. So the way you solve this is, for every mole of alkyne, you only add one equivalent of base so that you can only remove one proton. Yep. So by the time this electrophile comes in, there's no base around, there's just deprotonated alkyne. All right, so getting to the alkyne from ethanol is a slightly difficult series, and you may not remember that, though you've actually seen it before. It was on one of your problem sets. So this one might be easier to do in the forward direction rather than backwards. So you first need to convert the OH into a leaving group. You can choose anything that works, including PBr3. Then you need to do an E2 elimination reaction with a strong base that is not a good nucleophile. That will give you the alkene. Then you need to do alkene halogenation that will give you the vicinal dibromide. And just to remind you, this is a chapter 8 reaction. This is a chapter 9 reaction. Alkene halogenation is a chapter 10 reaction. And then, once you get to the vicinal dihalide, you may have forgotten this, but this is a highly useful reaction. If you use 2 equivalents of NaNH2 for every mole of vicinal dihalide, you can do the 2 tandem E2 reactions. And if you don't remember that this reaction, that's chapter 8.10 will tell you about that. That gives you the alkyne. Now, some people are wanting efficient and want to save space, and they're like, oh, if I use 2 equivalents, I get the alkyne. If I use 3, I go all the way to the acetylide, which is what I want anyway. So some people will show, instead of 2 different steps, first to the alkyne, then to the acetylide. Some people will draw an arrow that's like this, going straight to the acetylide with 3 equivalents of NaNH2. And that works, and you're free to do it. Okay? So now that we've mapped things out, and again, that reaction series, we could have gone through it in a retrosynthetic sense, but since you've seen a lot of those reactions before, and since I think it's probably still a little bit murky in your mind, I just wanted to walk you through it. Now, and I'm going to leave you guys to do this as part of your practice, I want you to map out the whole synthesis in the forward direction showing me what the reagents are for each of these forward steps. Okay? Once you've done that, you'll see how we connect starting materials all the way to a more complicated product. Okay, questions you want to ask about that? Yeah.
Do we need the OH that you checked when you're working backwards the first time, when you like turn OH into BR for the acetylide?
Yes.
Do we even need that, or should we just like put BR in there? Or like, do we reuse the?
So the reason we had to start with OH is because I made the problem more difficult for you on purpose. So you could ask, okay, Chuckles, why are you making me, I don't know why Chuckles is the nickname I use for people I'm irritated with on the road. Like, Chuckles over there isn't letting me merge or whatever, but anyway. And my wife was like, what are you talking about? Like, it's funny, isn't it? I don't know. But yeah, why didn't we just start with the alkyl bromide? That would have been an easier problem. And that is the answer to your question. Because then by making you go all the way to the alcohol, I make you remember stuff from chapter 9. Yep. So you're right, there are probably more efficient ways to do this. And the standard in synthesis problems, some of you are going to be like, why did you use the bromide? I prefer Socyl. Can't I use Socyl to make the OH a good leaving group? And I'm like, sure, your answer is right. With synthesis, the standard is, does your chemistry work? In general, you should be using reactions that we have done before. If you find yourself inventing chemistry, you're probably on the wrong track. Another example, actually, there's a way to go straight from the OH to the alkene. What about my good friend Pockle and pyridine? That does alcohol dehydration straight away. Yes, that would be even more efficient, so yay for you. And in fact, it's synthetic chemists, if you're the first person to synthesize a complicated natural product, then you get to publish an article in a really great journal and you say, this is the first total synthesis of this natural product, and you get to feel great about yourself. But a couple years later, somebody else is gonna publish a more efficient total synthesis where they get to the final product in fewer steps and with better yield, and that's the typical OChem flex. So you may find more efficient ways to do this. As long as your chemistry works, that's fine. This is going to be a little bit uncomfortable for you in practice problems though, because I might write an answer and your answer might be different, and then you're going to be like, is my answer wrong? Again, the standard is, does my chemistry work? So you may need to ask me or a TA, is this okay too? But in general, if you're using a reaction that we've talked about and it works, then your answer's probably right, unless you've missed some issues like we've talked about here, where the potential pitfall was, dealing with this OH group that could be deprotonated. All right. Yes?
So I assume for like test questions, you would have accounted for all of the ways that would work, and those are kind of going to be available in the options?
Right. So how does this appear on a multiple choice test? On a free response test, it appears exactly like this. And then you have to come up with it, and those problems are very, very difficult for the TAs to grade because there's so many ways you can do things, and there's also so many ways to get stuff wrong, and so it's kind of hard to grade in a fair way. I think this is a really good problem, and I think if you can do this, you've mastered the material pretty well. But in a multiple choice context, what I will typically do is I will give you a starting material and a product, and then I will give you options A through Z, but most likely A through F or E or something like that, where I will have a list of reaction steps. And you have to find the one that works. But be careful, I'm a real jerk about this. The ones that don't work will look like they work, but there will be something detectable wrong about them, something that would fail. And you have to pick the one that's right. In general, on these types of synthesis questions, that are formatted in this way, there isn't partial credit. In other words, you can't come to me and say, oh, well, you know, the one I chose got me part of the way. And I'm like, that is why you get 0 of the points, because the goal was to get all of the way. Okay, so you got to make sure in a question like this that all of the strategies work. Now, in this format, you don't necessarily have to do the retrosynthesis. You can do what a lot of people default to, which is, I'm going to try them all and then I'll pick the one that works. That'll work if you know what all the reactions actually do, and if you can think clearly, and if you can write out all the individual, step 1 gives me this, step 2 gives me this. If you try to do it in your head super fast, you're probably going to make a mistake. And you'll be better at it if you've done a lot of this type of practice on synthesis problems. Okay, so I need to start chapter 11, but let me just encourage you to practice synthesis. The way to do this is going to be go to the end of each chapter now, chapters 9, 10, and 11, and there will be a section of problems under the heading synthesis. If synthesis is hard for you, and it's hard for all of you, I can guarantee that it is difficult for all of you. Because over the years, one of the things people struggle with, they'll come in and what I'm really struggling with is synthesis. And I'm like, yes, you are. Welcome to the club. We all are. It's hard. So go do some synthesis problems and practice it. If you do that a little bit, you'll start to see patterns and it will start to become easier to you. If you just count on yourself having some kind of revelation in the moment, you got to give the Holy Ghost something to work with, folks. So put some of this stuff in your brain. All right. I want to just introduce chapter 11 now, which is on oxidation and reduction. And there are going to be a lot of reactions in this chapter, and some of them we will learn the mechanisms of, some of them we won't. But they're all really important reactions, and they will actually make it so that you can synthesize even more interesting products. I want to define oxidation and reduction for you in OChem terms. In Gen Chem, you learned that oxidation was what? Loss of electrons. That was your Gen Chem definition. That is still true, but it's going to be manifested via some key structural patterns. Loss of electrons? That's supposed to be an S. Okay. Whereas reduction is gain of electrons. We're going to see that in OChem, the loss of electrons in a molecule manifests itself as either a decrease in the number of carbon-hydrogen bonds and or an increase in the number of carbon heteroatom bonds, where heteroatom is oxygen, nitrogen, chloro, bromo, iodo, basically anything that's more electronegative than carbon. All right. In contrast, we're going to see that reduction is an increase in the number of CH bonds, and that reduction, and or a decrease in the number of carbon electronegative heteroatom bonds. So yes, go ahead.
Are pi bonds also part of oxidation?
So yeah, what about pi bonds part of oxidation? Yes, because incorporating a pi bond decreases the number of CH bonds. So you'll see an alkene is more oxidized than an alkane. All right, see you on Monday. Have a good weekend. At the end of the chapter, at the end of each chapter, if you'll look for synthesis, there'll be a heading that'll say synthesis and there'll be problems. Yep. Have fun.
With the synthesis, if we're using software mod, do we have to